In the previous lecture, we discussed the Bronsted-Lowry concept of acids and bases, and we extended our discussion till the autoprotolysis of water. Let me recall that slide. In autoprotolysis of water, we discussed about the amphiprotic nature of water, that is, water can act as both an acid and a base. We also introduced the autoprotolysis constant of water and discussed that pKw for water at 25 degrees centigrade is 14. And we also showed that the activity of hydronium ion at 25 degrees centigrade is given by the square root of the autoprotolysis constant of water, which comes out to 1.004 into 10 raised to the power minus 7 at 298 Kelvin. And then we further discussed that for 1 molar hydrochloric acid, the activity of hydronium ion is 0.81, and this 0.81, as I was discussing, it is less than 1 because you have to account for the activity coefficient. For pure water, we just discussed it is 10 raised to the power minus 7, and for 1 molar sodium hydroxide, it is about 10 raised to the power minus 14. And then we discussed that there has to be a simpler method of expressing these activities of the hydronium ion. There has to be a scale which should capture these activities of hydronium ion. And that scale is pH scale. pH scale is very, very important, especially when we talk about the biologically important system. pH becomes very, very important, because as we will discuss later on, the biological molecules, whether we talk about the proteins or we talk about the nucleic acids, pH becomes very, very important towards their conformational and thermal stability. We will discuss more later on about the conformational and thermal stability of biological macromolecules, but at present we are talking about the concept of pH. So let us discuss pH scale. How do we define pH? pH is defined as negative logarithm of activity of hydronium ion. Please note it is log, that means it is log base 10. And the correct definition of pH is minus logarithm of activity of hydronium ion. Please note, I am not saying concentration, I am not saying molality, I am not saying mole fraction. I am saying that pH is equal to minus log activity of hydronium ion. According to this definition, higher the pH of a solution, the lower its hydronium ion activity, because there is a negative sign over here. That means if the amount of hydronium ion or the activity of hydronium ion is very, very small, the pH is going to be high. Let us take an example. Can the pH be negative? Yes, the pH can be negative. For example, as shown over here, if we calculate pH for 2 molar hydrochloric acid, 2 molar, for which the activity is 2.03, the pH comes out to be minus 0.31. That is what I said earlier, if the concentration of hydronium ion or the activity of hydronium ion is very high, the pH is going to be very low, and vice versa. We can also define pOH scale. How do we define pOH? In the same way, pOH is equal to minus logarithm of activity of hydroxide ion. Here again this log is log base 10. pH and pOH are related to each other. For example, let us take an example of water. We defined the Kw, autoprotolysis constant of water, as activity of H3O plus hydronium ion into activity of OH minus. Let me take log base 10, log Kw is equal to log activity of H3O plus log activity of OH minus. And let me introduce a negative, multiply both sides by negative sign. Minus log Kw is equal to minus log activity of H3O plus minus log activity of OH minus, and this is pKw is equal to, this is equal to pH and this is equal to pOH. So you see, we develop a very important relation. pKw is equal to pH plus pOH. Let us go to the slide. Since Kw at a given temperature is constant, that means pKw is constant. If the left hand side is constant, that means if the pH of a solution goes up, the pOH has to go down to keep the sum constant. Since Kw is constant, pKw is a constant quantity at a given temperature. Therefore, pH and pOH have to adjust in such a way that the sum remains constant. In other words, if one goes down, other has to go up. If the value of one goes down, the value of the other must go up to keep the sum constant. For pure water, pH is equal to half pKw, because pH plus pOH are same. Therefore, pH will be equal to just half of pKw. Once again, because pH and pOH are same for water. Why I am saying is because the activity we just discussed in the previous slide, that the activity of hydronium ion and activity of hydroxide ion are same for pure water. Therefore, pH and pOH will also be same, which is equal to half the value of pKw is pOH. pH is equal to pOH. Next question is, does pH depend upon temperature? When we do experiments in the laboratory, is it important to mention temperature at which the pH is measured? Let us try to get an answer to this question from the next discussion. Let us go to the slide. The question is, does pH depend upon temperature? For this, we need to take a look at the expression for acidity constant, which we defined as activity of hydronium ion into activity of base divided by the activity of the acid. And as I discussed earlier, the acidity constant is actually an equilibrium constant, and the value of equilibrium constant is temperature dependent if delta H is either positive or delta H is negative. So, when the reaction is endothermic, the Ka value will go up with temperature. When the reaction is exothermic, the value of Ka will go down with temperature. So, therefore, if Ka depends upon temperature, the activity of hydronium ion will also depend upon temperature. If activity of hydronium ion depends on temperature, the pH will also depend upon temperature. So, let us take a look at the comments. At blood temperature 37 degrees centigrade, pKw is not 14, it is 13.68. And there, if you calculate the pH, it will turn out to be 6.84, not 7. That means when we talk about the neutrality concept, at blood temperature the neutrality will correspond to pH equal to 6.84. And since pKw is 14 at 25 degrees centigrade, at 25 degrees centigrade the neutrality corresponds to pH equal to 7. Use this value of pKw and set this equal to activity, Kw, you calculate Kw, and Kw is equal to activity of hydronium ion into activity of hydroxide ion, and when you calculate the activity of hydronium ion and hence the pH, it will come out to be 6.84. So, at blood temperature 37 degrees centigrade, neutrality corresponds to pH 6.84. At 25 degrees centigrade, neutrality corresponds to pH 7. So, this discussion clearly establishes that the pH does depend upon temperature. How do we calculate pH? Let us discuss about that. pH determination in laboratory requires the use of a pH meter. pH meter, what is a pH meter and how it determines the hydronium ion activity or concentration? It is a matter of a different discussion. You will learn it somewhere else about the pH electrodes, but let us here talk about the calculations. When we prepare solutions in laboratory, this I have discussed earlier also, the amount of different species in the mixture we usually calculate as molality or molarity or mole fractions. But the definition of pH is minus logarithm of activity of hydronium ion. Let us take a look at the slide. Since the definition of pH is minus logarithm of activity of hydronium ion, we need to talk about the activity. And when the solution is very dilute, then the activity coefficient can be taken as 1 and we can express or equate approximately the activity by the molarity or molality, whatever way you want to express. Mole per liter is molarity. And in that case, the acidity constant can be written in the form of concentrations. Since for very dilute solutions, we assume activity coefficient to be 1. And if that assumption is valid, then activities can be replaced by the concentrations and Ka can be expressed in the form of concentrations. And that is what is commented over there. It should be carefully decided if activity can be equated to molality or concentration or not. We need a small discussion over here. When I was discussing about the activity and activity coefficient, I mentioned that the concept of activity or activity coefficient is very, very important. Because when we talk about the experimental measurements, especially in the solutions which contain ions, electrolytic solutions, ionic solutions, even under very, very dilute conditions, the values of activity coefficients are quite different from 1. And therefore, activity coefficients cannot be ignored in ionic solution. And when we talk about the pH, the definition of pH itself is negative logarithm of activity of hydronium ion. Here we itself are talking about an ion. Therefore, the value of activity coefficient in these calculations become very, very important. And if we are absolutely sure, if we are sure that the conditions are so dilute, the solution is so dilute that we can treat activity coefficient to be approximately 1, then we can make the assumption as seen in this slide, that is, we are expressing the acidity constant in terms of the concentration. So, in elementary textbooks, what we see is the acidity constant is written as the ratio of the concentrations, and in advanced textbooks what you see is the acidity constant is written as the ratio of activities. So, therefore, please make a suitable judgment when activities can be replaced by molality or by concentration. Let us take an example. Calculate the pH of 0.2 molar HCN solution. Make approximation that activity coefficient of HCN is close to 1. So, we have been asked to calculate the pH of 0.2 molar HCN aqueous solution. Let us see how to approach this. We have HCN aqueous plus water liquid, and this is in equilibrium with H3O aqueous plus Cn minus aqueous. That is what is the ionization reaction over here. When HCN is added to water, you have this equilibrium. And we will write an expression for the acidity constant, which will be activity of H3O into activity of cyanide over activity of HCN. And we are given in the statement that the activity coefficient of HCN is close to 1. So, that allows me to replace this activity by the concentration. And if you look at into this equation, the activities are, see, the activity of H3O plus and activity of Cn minus, we can assume to be same over here. It is 1:1 ionization over here. So, I can write Ka is equal to activity of H3O plus square over, I am writing here concentration of HCN, because I am making use of the fact or making use of the statement that I can treat activity coefficient to be close to 1 for HCN. So, this therefore activity of H3O plus, if I rearrange this, is going to be Ka into concentration of HCN whole raised to the power 1/2. In order to calculate pH, I need the activity of hydronium ion, that is what I need. And you see how I have done. Wherever the information about activity coefficient was given to be almost 1, I have used that, otherwise I have retained activity. Now, let us go back to the slide. We were talking about this equilibrium in aqueous solution, HCN plus water forming H3O plus Cn minus, all in aqueous media. And we also wrote the value, the expression for Ka, and we came up with this expression, that activity of H3O plus is equal to the value of acidity constant into concentration of HCN, of course that is in mole per liter raised to the power 1/2. So, now what we do is, we have derived this expression, activity of H3O plus is equal to Ka into concentration of HCN, and in order to make it dimensionless, I will put mole per liter, and this is 1/2, and pH will be minus logarithm of hydrogen ion activity or hydronium ion activity. So, let me directly use that, minus log 10 activity of H3O will be equal to minus 1/2 log Ka minus 1/2 log concentration of HCN, and of course you divide by mole per liter. So, therefore, I can write this as pH is equal to half pK minus 1 by 2 log concentration of HCN, and I divide by mole per liter to make it dimensionless quantity. And let's take a look at the slide now. That's what I just derived, that pH is equal to half pKa minus half log of HCN concentration, and pKa of HCN is 9.31 and this concentration of HCN given to us is 0.2 molar, and after calculation you see the pH turns out to be 5. Now in this example we discussed how to do the calculations for pH. As I said that for elementary chemistry, these calculations may be okay, because in these calculations we have made assumptions. And what are those assumptions? Let us take a look at what are the assumptions made. The given information was make approximation that activity coefficient of HCN is close to 1. So first, activity coefficient of HCN neglected. That means if we want to really get a very accurate number, we cannot ignore the activity coefficient of HCN. Secondly, we have assumed that the activity coefficients of H3O plus and Cn minus are equal. That is what we did. We equated the two and took the square. In fact, these may not be equal. This is another assumption that we have made. The third one is, as I discussed in the previous lecture, that H3O plus, this itself, the contribution to this concentration, that is the amount of H3O plus formed from autoprotolysis of water, we have neglected, because water itself, as we say, we discussed earlier, due to autoprotolysis may contribute to some amount of H3O plus. So we have ignored those. Although if you calculate these three contributions, this may not be very high, but it may be still significant to be expressed as a very accurate value of the pH. So it is important to recognize that here in doing these type of calculations, we have made some assumptions, especially when we equate activities with the concentration, like AHCN is taken as the concentration, and that we did because the statement asked us to use that information, that approximation, that the activity coefficient of HCN is close to 1. So that is why it is important to keep in mind the approximations made, because if we are interested in doing very accurate calculations, we cannot ignore the values of activity coefficients, because after all we are dealing with the ionic solutions over here. So in this lecture we discussed a very important concept of pH. pH is defined as negative logarithm of hydronium ion activity, and this definition must be remembered. And then we must be careful when we equate activity with the molarity, molality or mole fraction. And with reference to pH, one will have to put the concentration. So therefore, we have to be very, very careful when we equate activity to concentration or activity to molality. And as we will realize later on, that when we discuss the biologically important system, how important the role of pH is in maintaining the conformational and thermal stability of the biological systems, as well as the various processes which are biologically important. So I hope that the concept of the pH is very, very clear, and it is also very clear that how to obtain or how to calculate pH by making some assumption, and also to recognize that when those assumptions can be made or when we need to really include the values of activity coefficient. Thank you very much.